All right, so we are talking about functions today and their corresponding graphs. Again, this might be some stuff you've already seen, but in math, you just got to kind of see it over and over and over again until you really get it. So we'll do a couple definitions. We'll talk about some examples. And I think, this section shouldn't be too bad. So first thing is, what is a function, right? So you've heard this definition before. And in mathematics and in trigonometry too. But, calculus, we care a lot about functions. And functions are quite important in mathematics. And why are they important? Well, so remember what a function does. So a function takes something from a group over here. This is my blob. We go from one blob to the other, right? So this is my function, and a lot of times we use F to denote function. Sometimes we use G and H. You've seen that probably before. And what does a function do? It takes something in this first blob. It applies a rule to that, whatever it is we're going to take. Let's say X, right? Because that's what we take. And we're going to take X and we're going to do something to X. Maybe we'll multiply it by a number. Maybe we'll add or subtract. Maybe we'll square it. I don't know. Maybe we'll get crazy and take the logarithm of it. I don't know. But we're going to do something to that X. Or maybe we're just going to leave the X alone. We could do that too. That's still a function. And we're going to do something to that X and we're going to spit out a number over here. So this is my function notation, right? You've probably seen this. This is not F times X. Remember, F does not represent a variable. It represents the actual function and what that function does, that rule that function does. So this F of X, that's what we say, F of X, right? And it doesn't, a lot of times in mathematics, of means multiplication. In this case, it does not mean multiplication. It just means my function evaluated at X. And it spits out this function value X. So what makes this special? So there are a lot of different things that we deal with that are not functions. For example, the circles that we were dealing with in the last video. That was not a function, okay? The reason that's not a function is the special thing. Here's a special thing about functions. For every time you put in this X value right here, this function right here will only spit out one F of X value, okay? So functions, the special thing about functions is for every element in the first blob, there's going to be only one element that it maps to in the second blob. And of course, what are we going to call these blobs? Domain and range, right? Now, we don't have to have to talk about domain and range, it doesn't have to be a function. It can be a relation, okay? But we are going to kind of focus on functions. So let's do the definition. So a function, and remember, you can't spell function without fun. I know. Stupid joke, but I like it. So a function is a correspondence. I'm going to go ahead and tell you right now I'm not a great speller, so I apologize if I misspell any of these words. Is a correspondence between a set called the domain. Okay, so that's my domain. That's where I'm starting from. And another set, which, what do we call that set? I'm going to imagine you're saying this. It's a range, Sarah. Is that bad that I might hear voices responding to what I'm doing here? So domain and range, those are pretty important terms. So we're going from the domain to the range, and this function is a correspondence such that each member of the domain, member or element we could call. Okay, so each member of the domain corresponds or is mapped to, you'll hear it say sometimes, corresponds or is mapped to exactly one element or member of the range. Okay, that is the definition of a function. That might be something that you want to know from memory, the definition of a function. So a function is a correspondence between a set, we call it the domain, and another set called the range, such that each member of the domain corresponds to exactly one member of the range. So for example, function or not a function? Let's look at some examples of this. We'll just do this with pictures first, okay? So let's say, this is pretty simple, but let's say that I have my domain are going to be the numbers 1, 2, 3, and my range in this case is going to be A, B, C, D. Okay, and so what I want to know is this relation that or this mapping that I'm going to show you, is it a function or is it not a function? So if I map 1 to A, 3 to B, and 2 to C. The way you want to check if something is a function is you want to make sure everything in the domain is mapped to only one thing in the range. Now that's a little weird, right? That kind of that terminology. So one thing that I like to say is one way to tell if something is a function is to ask, if I ask you what an element from the domain is mapped to, can you answer it in one word, right? Can you tell me in just one term what it maps to? So like in this case, if I asked you, what is 1 being mapped to? You just say A. If I ask you, what is 3 being mapped to? You say B. What is 2 being mapped to? It's to C, obviously. So is it a function? Yes, this is a function. This mapping that I provided here is an example of a function. Now, of course, I'm going to show you one that's not. So let's see, what about something like this? So what about if I did something like this? Okay, so an example like this, let's test again, is this a function? Again, if it is a function, if I list every element in the domain, you should be able to answer me the corresponding value in the range with just one word. So what is 1 map to? Maps to A, right? What does 3 map to? It maps to D. You can answer that. But when I ask you what does 2 map to, well, 2 maps to B and C. Do you see how I could not just say one thing? So the reason functions are important is we want to know for every input that there's one and only one output. I don't want any ambiguity there. I want to know exactly what it is. For instance, a function might be the temperature for the day. If I ask you look at your records, what was the temperature at 2 p.m., there's only going to be one temperature at that point, right? If we're at a certain latitude or longitude. It's going to be 87 degrees, right? That would be an example of a function. So this guy right here, this is an example of something that is not a function. Now, what if, one more example here, let me just keep using this kind of. So if I have, whoops, get out of here, yellow. If I have 1, 2, 3, okay, still in my domain, and I have A, B, C, D here. Tell me, well, you can't speak to me because you are in the internet. You're not in the internet, but would this be a function? Okay, let's look at this. Function or not a function? This looks a little bit weird, right? It's easy to see when it's a function when each thing is mapped to a separate value, but how would I test again if this is a function? I would ask myself, for everything in the domain, can I answer what it's mapped to in one word or one answer? So what is 1 mapped to? A. What is 2 mapped to? A. What is 3 mapped to? A. It is a function because what we care about when we care about a function is that everything in the domain is mapped to one element in the range. It doesn't tell us anything about the range having to have more than one element. It's not saying that everything in the domain is mapped to a different element in the range. If you go on into mathematics a little bit deeper, then that might matter. And when we could talk about inverse functions, that's going to matter as well. Sorry, my phone is going off. But it doesn't matter if everything in the domain is mapped to the same thing in the range, or if 2 things in the domain are mapped to the one thing in the range. Not a big deal. We just got to make sure that everything in the domain has only one friend. Oh, that kind of sounds sad. In the range. Now, could they all have the same friend? Absolutely. But everything, they can't have more than one friend. They got to have just one friend. I don't like that example. That makes me kind of sad. All right, so we kind of talked about some notation already. Let's see here. But some notation, you know, is probably, you've seen this already. So some of the notation we have is, you know, this f of x. We already kind of talked about what that means. But for example, if I had f of x, then is this function 2x minus 3x squared. Okay, that is a function. We don't know quite what that looks like yet, but you might know if it's a quadratic that it's kind of a parabola. And it makes sense that it's a function because if I put in an x value, I'm only going to get one y value out, or one function value out. Because when I multiply 2 by that x value and then I subtract 3 times its square, it's not going to give me like 2 different answers. When do we get 2 different answers? Like sometimes we'll get 2 different answers when we have something like y squared equals x, something like that. Like if x was 4, what numbers could go to 4? Well, 4 could be mapped to 2, or it could be mapped to -2, right? Because 2 squared is 4, but -2 squared is also 4. That's an example of something that would not be a function. Okay, just wanted to give you an example of that. So some function notation, if I asked you to evaluate f of 1, right? What would we do to evaluate f of 1? Well, what that means is everywhere I see an x, I'm going to put whatever is in those parentheses. That is what function notation is. Don't forget order of operations. I'm going to square the 1 first, which obviously is 1. I take 2 times 1, which is 2. 3 times 1, which is 3. So we get a -1. What about f of, you know, -2? So I would have 2 times, again, everywhere I see an x, I am going to be putting whatever's in those parentheses. That's what that notation means. This is basically asking, what does this function do to -2? What does it map it to? All right, let's do some order of operations here. I get -4 minus 3 times -2 squared is a +4, right? So we get -4 minus 12. So we get -16. What does this tell us then? That what does my function do? What is its rule? It takes -2 and it maps it to -16. One more just for fun. What if we have m minus 3? Oh, now we're getting crazy. Sir, you're crazy. I know. I understand that. My kids tell me that all the time. I'm all right with it. Oops, sorry, but look at what I did here, guys. I took this m minus 3, right? Wherever I see an x then in my function, I'm going to replace that x with the m minus 3. That's what function notation means. Distribute this 2. I can do that because I'm not doing addition or subtraction yet. What must I do here? Don't you dare take that -3 through. Okay, I'm sorry, that sounded a little mean, but you better not. Also, don't you dare distribute that exponent. What does m minus 3 quantity squared mean, people? I think this is like the pet peeve of every single math teacher I know. Squared means to multiply it times itself. Think about what these things mean. I know I'm asking you a lot to think, but think about what these things mean. Squaring means I multiply it times itself. So m minus 3 times m minus 3, I'm going to do a little bit of foiling. A little bit of foiling in the morning or afternoon is always a good time. Combine like terms, you should be able to FOIL. I get m squared minus 6m plus 9, and now I need to take that -3 through, right? So -6 minus 3m squared, hopefully you remember all of this, plus 18. Don't forget to take the negative with you. The negative hangs out. The negative is part of the 3 basically. And now we combine like terms, and just because I have issues that you don't need to worry about, I have to write it in descending order because it bothers me if I don't. And I hope I didn't make any arithmetic mistakes because that's where I usually make my mistakes, or with arithmetic. So I hope that makes sense. You know, when we talk about domain and ranges, it doesn't always have to be a function. It can be a relation, meaning just a rule that assigns values in the domain to values in the range. And that's okay if it's not a function. It's just most of the things we're going to focus on are functions because they're nice, because we don't have to worry about, but we don't have to worry really about, you know, wondering what everything in the domain goes to. So I hope that makes sense. Let's see, what else do I want to talk about really quick? Let's talk about the vertical line test, and then we'll talk about finding domains, and then that's kind of it for this section. So that won't be too bad. So really quick, let's write down the vertical line test, and then we will talk about what it means. So the vertical line test, so we talked about kind of these functions and what they mean, but what does that mean if we look at its graph? So the graph, remember, of the function is just all the ordered pairs on the Cartesian coordinate system, right, that are solutions to that equation. And so that's going to be, so if I look at my functions, if I were to put in a bunch of x values and their corresponding y values, right, those numbers that are spit out, it would create a graph on the Cartesian coordinate system. How would I determine if the graph I'm looking at is the graph of a function? So that's where we have what we call the vertical line test. So let's write it down, and then we'll talk about why it's true. So, not the a graph. Whoops. A graph, the graph that you're given, is the graph of a function. Whoops. I'm sorry, I really have done this before, is the graph of a function if every vertical line, not just one, but every vertical line, right, intersects the graph. And at most 1 point. Okay, and at most 1 point. Okay, so what does that mean? All right, I'm gonna freehand some graphs here. This is gonna be good. You're gonna like it. You're gonna like that I can't draw straight lines. Okay, so for example, let's say I have some pretty, okay, this is like one of my favorite looking graphs. It goes up like this and up like that. Okay, this is some sort of, we'll talk about this later, this is some sort of cubic function. It's a polynomial of degree 3. So let's look at this graph. Is this a graph of a function? Well, what the vertical line test says is if I take any vertical line, so I could draw, right, an infinite number of them, pretend these are vertical and pretend that they're lines. So any vertical line, as long as all of those vertical lines pass the graph in only one place, see how these are all passing in only one place, then we're guaranteed that this is the graph of a function. Why is that true? Well, think about these vertical lines. Remember, this here is my x-axis, this is my y-axis, or we could think of it as my f of x-axis, or my function values that we're spitting out. What is this point right here? Well, what is the point? Man, that question is asked all the time. This point right here is x comma y, or in this case, remember y and f of x are kind of the same thing. This is x, and then my function evaluated at x. If I draw a vertical line right here and I only intersect in one spot, that tells me that that x value is only mapped to this one y value right here. So it is going to be a function, okay? Because all these vertical lines basically represent every single possible x value. If it only intersects in one spot, that tells me I only have one y value corresponding to it. Let me show you something that does not pass the vertical line test and why that would make sense then that this, ooh, that wasn't very pretty. That this would not be a function. So let's say I had something that did this. Well, actually, let me put that somewhere else where it's not right on the y-axis. So what if I had something that did this? Okay, so I have something that does this, and if I take, let's just draw some vertical lines. Again, pretend they're lines. I told you that this class is a class in imagination, right? So remember, these vertical lines are basically grabbing all of these x values along the x-axis, right? And we're going to test these. And so if I look at what this graph is doing, if I put in an x value right here, right, that x value corresponds to one and only one y value. Same here, but you can see this here. Look at this guy. Okay, this x value right here has a y value corresponds to this y value, and it looks like it corresponds to this y value, and it corresponds to this y value. So this x value right here has more than one friend. That's not good for a function. Okay, it's not a function then. This x value has more than one friend. I can actually see like right here, I'd have another x value that would have more than one friend. So not a function. This guy is not a function. I make that sound like it's a bad thing. This guy is a function. It's not a bad thing. Like in mathematics, we use things that are functions all the time, not functions all the time, like circles, right? Circles are not functions and yet are quite important in mathematics. However, when we start talking about like inverse functions, when we start, really working with things, we want functions because we want to guarantee that whatever our x value is that we put in, the y value that we get out is the only y value that we get out, okay? So like your grade should be a function. If I assign each person in my class a grade, I shouldn't assign you an A and then also assign you a C. That wouldn't make sense, right? You'd be like, but wait, what is it, Sarah? Is it an A or is it C? I'm like, I don't know. I decided to make my grading not a function, right? That doesn't make sense. So that's why we care about functions in mathematics, not to say that things that aren't functions aren't important as you get higher in different math classes. I hope that kind of helps. So vertical line test, easy way to just look at the graph of something and determine if it is a function or not. Okay, so I want to look at a couple more examples and then we will call it good. So finding domains. Let me clear out this guy right here. Finding domains algebraically and then graphically. So let's look at actually, I'm going to switch that around. Let's look at graphically first. And ranges. Let's do ranges. Okay, so what I want to do is I'm just going to show you a graph, and then you determine, find the domain and range of each. And what we're going to do is put our answers, let's put our answers, I'm going to look in your book really quick. I believe they like your answers in interval notation, but I'm just going to check out your book right here. Yeah, we'll do interval notation. Actually, let's do both. I'm going to show you set and interval notation, okay, just to make sure we get the correct thing that we want. So let's look at this graphically first. So what if I had a function that did something like this? Just gonna make my own axis here, and we're gonna make this kind of easy. We'll just kind of go like that. And this is going to be, not perfect at all. So my domain. So when we're looking at a graph and we want to know the domain of my function, what I want to look for is I want to see what x values. Remember, x are my horizontal. Range are going to be my y values. Okay, so domain are my x values. Range are going to be my y values. That's what I'm mapping to. So if you look at this graph right here, what is my domain? What x values actually have a little purple dot association with it, right? These are just all an infinite number of dots put together. So if I look here, it looks like the smallest x value that I have associated with it is -2, and the largest 1, 2, 3, 4, 5. Remember, I'm not looking up and down for this one. I'm looking left to right because that's my domain. So it looks like all my x's from -2 to 5 have y values associated with it. So I would say my domain. Then remember, in interval notation, I'm going to go -2 to 5. And remember, interval notation, my left-hand number is the smallest I can be. My right-hand number is the biggest I can be. I use these square brackets or square parentheses kind of if I include those. I use open brackets if I'm not going to include them. So I do have values at -2 and at 5. So I use those square brackets to make sure that I include those. What is my range in this case? So now my range, I'm going to look up and down. So at this point right here, what is the lowest it gets here? That's -2. And then I come all the way up. I'm getting all these y values in between up until this point right here, which is 3. Range can be kind of tricky. So practice these. My range, then what y values am I going to get? -2 to 3. Again, domain are my x values. Range are my y values. I hope that kind of makes sense. Okay, what about if I had, let's look at another example. I'm just going to kind of shove it right here. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. I'm going to make something up here. What if we went here to here, and then maybe here to here? I don't quite know what this is. Is this a function? Yeah, it passes the vertical line test, right? This is a little wonky here, but it's supposed to be a function. So let's look at my domain. Again, what is the smallest x value? It looks like -4. Now we have to be a little careful with this one because look at, I have x values from -4 up to, what is this right here? -2, right? I have a graph there, but look at between -2 and 0. Do you see how I don't have anything in between here? So I can't include -2 to 0 in my domain. Then at 0, I pick it back up again until 3. So my domain, I'm going to do -4 to -2, close, wow, that's supposed to be a closed bracket. Sure doesn't look like it. Close bracket, union, remember that's how we join. Okay, this is going to sound stupid, but this is going to help you remember. You want to do union when you want to unite the two intervals together. So union just means I want this interval and I want this interval. So I'm going to unite them together. I know, stupid, but you'll remember it. Union with or united together with 0 to 3. Notice I don't have any graph in between -2 and 0, so I cannot include that in my domain. All right, for range, let's see what we got going on for range. It's going to be a little cray. Do kids say cray anymore? Probably not. -2, right? Look, I have all these y values of -2. Then I don't have any y values between -2 and 0. That's funny that I got that. Then as I, remember I'm going up and down. Then as I come up, I do grab 0, and then I get all my y values. What's the highest I get? Up to 3. So my range then, sorry, I didn't mean to do that, is going to be on this one. This is kind of weird. Sometimes if we just have one number, we just put it in this kind of set notation. I call them squiggly brackets. I don't think that's like technically the right term. It's probably not. Squiggly brackets is probably not like a mathematical term. And then 0 up to 3. Sorry, that's the same as the domain. I probably should have made those a little bit different. But so again, look at my range. I have -2, just that number by itself. So I use squiggly brackets to indicate that's just one number. And then what is my range? Up from 0 up to 3, union 0 to 3. Hope that makes sense. Try those. They'll be on your homework, and try some of those from the book. They're kind of interesting. All right, and now let's talk really quick, almost done, you guys, about finding domains. Domains algebraically. We're not going to look at ranges algebraically right now, but we will later on. Algebraically. I feel like I spelled that wrong. That's wrong. And that's a little embarrassing. I don't think that's how you spell algebraically. Oh well, I'm gonna leave it, and you guys can make fun of me, and that's fine. I'm good with it. All right. So, domains algebraically. Here's what I'm gonna tell you. We worry about dividing by 0. And negative values under even roots. Or even roots, even radicals. Okay, you guys, where could things go wrong, right? That's what we want to look at when we're looking at the algebraic form of a function. So the algebraic form for a function is just that rule, right? Like 3x squared minus 2. What we want to look for, here's what you got to worry about when you're talking about domain with algebraic functions. You have to worry about fractions and you have to worry about even roots. Pretty usually square roots, right? Because that's the normal one we do, but 4th roots, 6th roots, 10th roots. We worry about dividing by 0 and negative values under even roots. So if you do not have a fraction or if you do not have something that could give you a 0 in the denominator, if you do not have something that you could get a negative under an even root, you are good to go. Everyone is invited to the party. Okay, so let's look at an example, a quick example here. F of x equals x squared minus 2x minus 3. Remember what domain is. Domain are your x values. So what you want to look at when you're looking at domains is, are there any x's that I need to leave out? Are there any x's that are not invited to the party, right? They don't get along with people, they make a scene. We don't want those x's to come to the party. So again, what are the x values that would cause us any issues? Any x's that would cause us to divide by 0, or any x's that would give me negative under even roots, are x's that I'm going to not allow in the party. Let's look at this function right here. Can I square any x value I want and not divide by 0 or have a negative under an even root? Absolutely. Can I multiply any real number that I want by 2? Absolutely. So what is the domain of this? Everything. Everyone is invited to the party. So we're going from minus infinity to infinity in set notation. So this is interval notation. Okay. Set notation would be all x. Set notation says, all right, here are my x values, but there's a little bit of a stipulation on x, and that's what we mean by that line. That line just indicates it means such that x is a real number. Okay. Or if you want to look cool in front of your friends, this is going to show you you're cool in front of your friends. Let me tell you, being able to write it like that. X and this little backwards E is an element of, and this is a bold R for the real numbers. So everyone is invited. Let's look at this. What if this was my function? Okay, now we have some issues, right? Granted, you know, it's okay, everyone has issues. I have issues. But this function has some issues if we're talking about domain. I want x's that are not going to make me divide by 0 or negatives under even roots, because right now those values are not defined in the real numbers. Dividing by 0 is never defined. Later we're talking about negative values under even roots in the complex numbers, but we have issues with that stuff. Bad stuff happens, right? It doesn't make sense in mathematics for those things. So here, the problem is I have a fraction. It's not a problem, but it's something I have to consider when I'm looking at domain. Are there any x values that would make this denominator 0? Well, I don't know. I can't just look at that and know. So what I'm going to do is I'm going to take my denominator and I am going to set it equal to 0. If I find any x values that make that sucker 0, those x values are not invited to the party. Okay, so I'm going to factor this. You remember factoring. Two numbers that multiply to be -3 and add to be -2. So what do we get here? Oh, look at what we found, you guys. We found that 3 and -1 cause the problem, okay? They're the people that continually get in a fight with the other numbers at the party. It's not cool, guys. No one likes those people. So we have 3 and -1 are not invited to the party, because if we took 3 and -1 and we plugged it into x squared minus 2x minus 3, it would make that expression right there 0, which in turn would make f of 3 1 over 0 and f of -1 1 over 0. That's not good. Not good. All right, so here's what my domain is. So in set notation, let's do set notation because I think that's the easiest when you're just leaving out a couple numbers. So here's the thing. All x's are invited. This is what set notation is telling me. Everyone's invited except, right? That's what that line is, except -1 and 3. Everyone can come except -1 and 3, because -1 and 3 are going to give me a 0 in the denominator. In interval notation, think about this so interval notation, really just picture this on the number line. What we want to do is we want to just leave out -1 and 3. So I want everything here. I want everything here, and I want everything here. I just don't want those in between. So from here, this guy right here, I'm going to represent minus infinity, open parenthesis because I can never equal infinity, to -1. I don't want to equal -1. I just want to get really close to it. this part right here, union, unite these guys together, -1 to 3, right? Union, and then this guy right here would be 3 to infinity. Noticing that I'm not doing square brackets because I don't actually want to include -1. I don't want to actually include 3. Could I include 2.9999999 though? Yeah, absolutely. That's why I want the open parenthesis. This again is set. This right here, my friends, is interval. Okay, one more example and then we'll be done. One more example. So again, dividing by 0 and square roots, negatives under even roots. What about something like this? The square root of 5 minus x. Who's invited to the party? So because this is an even root, right? There's a little 2 there if we don't put anything. I know that if I want to stay hanging out in the real numbers, which we want to do so far, I need this guy to be bigger than 0. So what I'm doing is I'm just actually going to take everything under the square root. I'm going to set it greater than or equal to 0. Could it equal 0? Sure, in this case it could. I don't have a fraction. So I can equal 0 as long as I don't have a fraction, right? As long as I don't have a 0 in the denominator. So what I like to do here is just add x to both sides. Then I don't have to worry about dividing by a negative or anything. So look at what this is saying. That 5 must be greater than or equal to x, or another way to say that is that x must be less than or equal to, no, not x, not x, less than or equal to 5. So if I look at that on the number line, here's 5. That was a nice picture, huh? I need to be less than 5. Okay, so interval notation, minus infinity up to 5. Can I equal 5 in this case? Absolutely, I can equal 5 in this case. There's my interval notation. This is my domain. Or in set notation, all x's are invited except there has to be a little bit of a stipulation on what x's can come. Those x's must be less than 5. Because if they're not less than 5, if they're bigger than 5, we have some people who are not very nice at the party. Like if I put in 6, I get 5 minus 6, which is -1. One last example. I can't help myself. What if I had this? F of x equals x over the square root of 5 minus x. Now, I know I have 2 things I have to consider. I want to kick out anything that's going to make the denominator 0 and anything that's going to make this square root negative right underneath. So what am I going to do then here? I'm going to take 5 minus x, and instead of setting it greater than or equal to 0, I'm just going to say it has to be strictly greater than 0. I want to leave out anything that would actually make it equal to 0. So this example is going to be very similar to the one up above. I just now have the strict inequality that x must be less than 5. So my domain then is going to be minus infinity up to 5, but 5's not invited. Everything close to 5 is invited. Poor 5. But I can't actually grab 5, right? And I'm done. This x right here, can that x be 0? Sure, why not? I can have a 0 in the numerator, just can't have a 0 in the denominator. All right, you guys, that was fun. Let me know if you have any questions.